Today we are explaining T2MLR, a transformer architecture for carrying intermediate reasoning states from one generated token to the next.
What is the central problem with ordinary autoadhesive reasoning?
A transformer may perform rich hidden computation while generating one token, but the next step receives only the discrete token and its embedding. The useful intermediate state has been compressed through the vocabulary interface. For a multi-step problem, the model repeatedly rebuilds reasoning that could have been carried forward directly.
Why do existing methods for carrying hidden computation not solve that bottleneck cleanly?
Earlier latent reasoning methods usually feed a final layer state, or a soft token mixture back through the input embedding, so the recurrent signal still bypasses the middle layers. Loop transformers can create more computation, but they repeat layers during inference, making each generated token more expensive. The unresolved question is where recurrence should live, and how to train it with dense supervision without losing sequence-level scalability.
So what is the specific architectural change in TMLR?
T2MLR keeps the ordinary transformer and adds a constant size recurrent cache. After token T passes through a chosen middle block, the model stores that middle layer representation. When token T plus 1 arrives, the cache is fused into an earlier layer of the new token. So abstract computation crosses time without crossing back through the vocabulary.
Which part of that diagram is doing the actual memory transfer?
The green fusion module combines the current token representation with the previous cache before the recurrent middle block. It has a residual path, an input-dependent gate for the current stream, and another gated projection for the recurrent stream. The cache is then updated after the block with an RMS normalization of the new middle representation plus the old cache. The gated fusion used by T2MLR is written as follows. He reaches the current representation before the recurrent block and is the previous cache. The two sigmoid terms select features locally, while the tan gamma factors control the overall strength of the current and recurrent paths.
Why does the cache update include the previous cache instead of replacing it outright?
The temporal residual lets information accumulate across decoding steps, rather than forcing every new middle representation to start over. The update is RT equals RMS norm of H at the end layer plus RT minus 1. RMS normalization keeps the scale controlled, while the addition preserves a running latent state that can be refined token by token.
A recurrent dependency usually breaks the parallel training that makes transformers practical. How does TMLR train?
During teacher force training, T2MLR uses a fixed number of Jacobi-style refinement passes. A first parallel pass supplies an approximate cache for every position. The model fuses those cache states, reruns only the recurrent middle block, shifts to new states in time and repeats. The final refined cache supports the normal forward pass, while truncated backpropagation limits how far gradients travel through the recurrence.
What does the first control task test before the broader language experiments?
The S5 retrieval benchmark combines two abilities that favor different architectures. The model must track a running composition of permutations, which requires state to persist across a sequence, and then use a randomly resampled dictionary to retrieve a string for each current state. A shallow transformer has retrieval but limited depth for state tracking. An LSTM tracks state but must compress the dictionary into a fixed size memory. T2MLR is designed to combine both paths.
What pattern separates the three models in the plot?
The LSTM and transformer baselines have essentially zero exact match accuracy across the tested lengths. T2MLR stays near perfect through the lengths seen in training and keeps substantial token accuracy beyond them. That result matters because an exact match is unforgiving. One local error ruins the whole sequence. The recurrent path preserves the evolving state, while attention still gives access to the dictionary for retrieval.
Does that advantage survive ordinary language model training, or is it only a synthetic task effect?
It survives pre-training with parameter-matched models on 10 billion fine WebEdu tokens. The baseline average score on the 7-0 shot benchmarks is 42.83. The strongest T2MLR configuration, recurring through layers 13 to 18, reaches 44.1 for while looping over only 6 of 30 layers. Full layer recurrence is weaker, so more recurrence is not automatically better.
Why is the location of the recurrent block more important than simply making it larger?
The authors hold the recurrent width fixed and move the block to early, middle, or late layers. The middle placement wins on the zero-shot average at both tested widths. That supports the motivation. Early layers process lexical and syntactic information. Late layers map toward the output vocabulary. And the middle is where abstract reasoning is most active. Recurrence is most useful when it carries the state from that computational region forward.
What happens after fine-tuning these pre-trained checkpoints on actual reasoning tasks?
Across variable assignment, graph connectivity and POS-QA, multi-hop hotbot QA, and both symbolic and natural language GSM August, every T2MLR variant beats the parameter and data match transformer baseline. The improvement is not limited to one task. Middle layer configurations consistently beat full layer recurrence, showing that the same depth choice that helped language modeling also helps multi-step reasoning.
Can a practitioner add this pathway to a model that is already trained?
Yes. The largest experiment inserts the recurrent fusion pathway into the instruction tune small LM to 1.7b model and fine-tunes for 1 epoch on open math reasoning. GSM-8K accuracy rises from 35.78 to 39.88, an 11.5% relative gain. MATH 500 rises from 12.80 to 18.00. The architecture therefore improves reasoning without a new pre-training run.
What does that cost during training and inference?
Training is the cost. The parallel refinement tree runs the recurrent middle block several times, making training roughly 2 to 4 times slower depending on block width. But autoguessive inference does not run those Jacobi iterations. The measured per token overhead stays below about 8%, and the added recurrent state uses less than 0.1% of peak inference memory.
What should we be cautious about when interpreting the results?
The paper is strongest as evidence for an architectural and inference side advantage under matched parameters data and inference compute. Under a matched wall clock training budget, a longer-trained ordinary transformer can surpass the 135 million parameter T2MLR model on zero-shot language benchmarks. The authors also call for larger models, harder reasoning suites, multiple random seeds, and a better understanding of what the recurrent pathway stores.
Then what is the paper's main claim in one sentence?
T2MLR shows that a transformer can preserve useful latent reasoning across tokens by carrying a middle layer state directly into the next token's computation. The evidence points to a precise design lesson recurrence is not automatically strongest when it covers the whole network. It becomes more effective when it is placed where abstract reasoning is already being computed.
So the contribution is a targeted recurrent shortcut, with stronger reasoning on nearly standard inference cost, but a real training time bill.
Exactly. That wraps up our explanation of T2MLR transformer with temporal middle layer recurrence.